If you're anything like me, you can follow a tutorial where they say to right-click this and add that and enter this number in this box, but you might find yourself craving more knowledge like I did when I was building a simple bot where I added a wheel. I needed to understand how the joints work and why I was entering those values. So that's where I decided to go down the rabbit hole and reverse engineer all of the joint examples in Isaac Sim. And that is exactly what we're going to do in this video. We're going to reverse engineer each of the example joints in Isaac Sim so that we can understand how each of the settings within them works and how that affects the joint's movement. My personal journey began with making whatever this is. Me playing with settings to understand how things work. Eventually, I felt I understood enough to confidently create one of my favorite beginner bots, but that still only used the Revolute joint. But as you can see with this hand that I made, well, it's a rough hand, but it's made with nothing more than Revolute joints, so you can still do a lot with that. We're going to start with something simple like the fixed joint, and then we'll move up to the Revolute joint, and we'll go over the other basic standard joints like the prismatic and spherical. And then when we're done with those, we'll do a high-level overview of the specialty joints that Isaac Sim has available and how those might be used. Before we get started on the fixed joint, let's set up the scene so that we have everything in place. So I usually start off with just the default light. I know you initially need a ground plane so that you have something to get the physics. You can start with the physics scene so that you can set the gravity, but you'll also need a ground plane. Go here. And let's just rotate that so we can see that a little better. And so that gives us the basics. And to access the physics examples, let's just open that up since we're here. I've got the physics demo examples here, and that's where the joints are. It's right inside of there. I already had that open. And one other thing that we're going to want to do is be able to see joints. We're going to set this show by type. Go down to physics and hit joints. We don't have any joints in our scene yet, so let's create that. For the fixed joint, we can do a simple cube. We'll want to right click that cube and add rigid body with collision preset so that if we pick that up and we hit play, it will fall to the ground. Now we can duplicate that. Just right click and hit duplicate. Ooh, look at that, it pushed itself out. Let's go ahead and move it over the other one. Oh, I'm still running the simulation. See, I love the simulation, how you can actually play that. Let's move these up out of the way here. Get this off the ground. Put this one down on top of the other joint. Well, we'll make a joint between these two blocks. Tilt this up so we can see it. I'm going to go ahead and rotate this so that we can see the difference between the two. You want to select your base cube first, then hold the control key down and select the other cube. Now you can right click and hit create physics joint fixed joint. And what that's done, and since we had that setting here so that we can view our joints, you can actually see that in here. And if you click on that, it will show you all the parameters about it, and you can come down here and see the different physics settings and things. But since this is a fixed joint, nothing's really going to happen. All it's going to do is fuse these two pieces together. Oops, I'm grabbing the wrong piece. Don't grab the joint. Grab one of the cubes. Here we go. So now if I pick this up and drop it, let's pick it up and drop it, like make this thing go somewhere. So now you can see no matter what I do to it, these two pieces are fused together, and so you can see the orientation does not budge. As far as I can tell, it seems like it's moving around pretty well. Yeah. So that's pretty much the fixed joint. Nothing fancy. Let's move on. For the Revolute joint, which is the next on our list, I'm going to go ahead and open up the example. And that's what's going to bring us into this nice little room to help you kind of get orientation. I don't know, kind of orient you to the environment so that you know which end is up, I guess. But if you click this Revolute joint now, because we had that settings, that joint view set, we can actually see the parameters again, which are just really valuable here. This is really an important piece to understanding the joint, because now you can come down to the Revolute Joint's axis and change it to Y, and you can also change it to Z, and you can see what's happening. If you zoom in on Y, it just creates a, let's go, I need to click on that scene so I can click in there, and now because the Y axis is picked, if we hit play, it rotates the beam versus the way it was originally. Let's just change this. Set to X. When you hit play, it's going up. Why, you might ask? Well, that's because of the different settings on this to drive it, and we'll get into those in a second. I just thought it'd be kind of cool to show the axis first. And so now you can see the Z axis, and then it will shift to the left or the right, depending on what you set. So let's talk about those settings a little bit on the Revolute joint. There's multiple, I apologize, when I'm running on a small graphics card, and sometimes my stuff wigs out. But let's see here. If we look at these two beams, one of the main things that I started understanding was the difference between local position and the local rotation for 0, which is body 0 here, and local position and local rotation for 1, which is body 1. You can see that's box 1. And box 1 in this is the blue one. Box 0 is the red. And I got to click back on the joint so you can see their relationship here. You'll notice that there's some values in here, and that's where, when you're following tutorials, they just tell you to enter those values. But if you look at box 1, you'll see that it's 120 pixels, or 120 meters, I believe is the standard setting here for Omniverse. If we shifted this to be 100, let's just say 102. I think that was one that I think works. Oh, there goes. Sorry about this. Now you can see that the joint is offset, and there's also a red arrow telling you, hey, you need to align the bodies. That's what these will help you do. Because we're at 100 and not 120 now, if you change this to 51, and this one, you'll see that there's a silhouette of the beam here on the box 1 beam. If we change this one to -51, now you'll see that red went away, and what it did is it brought that silhouette of the beam together. And what happens if you don't do that, when you hit play, it will jump to that marker here. So you can, oh man, this is just going to be bad. There you go. So you can see it's jumping to that marker from the silhouette, like the ghost beam, I guess we'll call it. That's what happens when you have this red. And actually, if you look at the logs, you'll see that there's an error being logged. Not an error, but a warning telling you that there's a problem. So that's where, if we can set this to match the position of our beam, then it works better. Now, one of the other things is that you can start to see these two as they work together, especially if you're doing a digital twin and you want to see how the two pieces connect and what effect it has on the joint. Oh, this is really cool. Check this out. We know we're going to have these two are going to hit when we hit play, but watch what happens. The joint gets stressed a little bit and it actually separates, so you can see that. And that is the coolest thing, I thought, because that is where these digital twin simulations are going to be helpful, because at that point you can set braking parameters to actually have that joint break under a certain amount of stress. But let's worry about breaking joints later. For now, let's go ahead and zoom back out, and now that we have a good understanding of how this joint works and some of the errors that we were seeing, let's delete this joint and see what happens if we recreate it. So really what we do is hit box 0, hold down the control key, hit box 1, right click, and hit add physics. Whoops, we need to create physics joint. Sorry about this. Create physics joint and Revolute joint. And there we go. Now you notice the position of this is in a completely different place. So if we hit play, nothing happens because there's nothing to move. So because it's basically stuck in the center of gravity on this beam. So if we can click this and zoom in here and pull this back to about here, let's see what happens. There we go. Now we're falling. And that's basically just gravity taking over because we've moved it to the center of gravity. Let's move it back just a little bit. So what happens if we go to the edge of this? Now we got like a pendulum type of scenario. So you can see that the center of gravity is really important. But since we want this to technically be right between these two, we can zoom in. Let's see how close we are to the center. Somewhere in the middle. Here we go. You can see that guideline here helping you see the connection. And if we hit play, it's going to drop like I think I want. The only thing I like is having the collision enabled so that when it hits, it bounces. And that's where you see that stress on the joint. And this is just from gravity, no drive whatsoever. Since we kind of want to recreate the original example, let's go ahead and add a drive by right-clicking on the Revolute joint that we created and say add. Go down to physics and say angular drive. And that's where we can control change the force or acceleration, set a max force, target positions, target velocity, dampening, and stiffness. Now, to get an understanding of what these do, you would think if I want it to go up, we've got the Revolute joint set to X like we had it before, and you think, okay, well, let's just add some velocity and say, let's just go 50. And you'd think, what happens if I do that? Does that make it go up? No. Why is that? Well, because you gotta have dampening, which is essentially kind of like a shock absorber that sort of happens in a real drive, and without it you don't have any tension. So let's go up to like 1,000, somewhere in there. Nope, not enough. It takes a lot. And hit play. There we go. Now we're climbing. So what we're doing is working our way against gravity. We've got target velocity, but the motor itself didn't have any dampening, and we needed to add that. So let's just cut that down a little bit, see if we can clear that. Hit play again. We're just dropping, and we can go 1, 2, 3, 4, 5 zeros, and we start to climb up. We can change our velocity now. Actually, we took away the velocity, and what's happening is gravity is dropping it, but because the dampening exists, it's slowly dropping. That was a cool thing to learn. And I'm not a mechanical engineer, so this was all news to me. I didn't understand how this works, but now I can add a smaller amount of velocity, like 20, and have it slowly go up. Or take it away and have it slowly fall just based on gravity, or remove the dampening altogether and watch it drop. So that's pretty cool that you can change those settings during the simulation. I do believe that sometimes those aren't saved when you're running them in the simulation, because those are usually control parameters if you're doing a digital twin. So I think at this point, let's go ahead and move on to some of the custom variations of Revolute Joint that I figured out. Alright, so to take the Revolute Joint to the next level, we're going to go ahead and create a new scene. And we'll just create an empty one. We don't need to save this. This is just exploration. And we shall set the default light. Make sure we create a ground plane for physics so that we can see that. Alter that so that we can See where things are going here. And I don't know. Let's try by creating a. Let's do a sphere. This is kind of an interesting thing. I'm going to create this sphere off the ground. And kind of like in that last example, you could see the beam that was floating. That basically means we're not going to apply any physics to this sphere. But what we'll do is duplicate it. Duplicate. And we'll put this sphere off to the side somewhere. This one, I'm going to go ahead and apply some physics to it and say, whoops, we got to go to add physics and add that. And now we can see this sphere drops. But what's interesting now is that I can click this sphere, the main center sphere, we'll call it, right, hold down the control key and click sphere 0. And now I can create that joint. We'll go down to physics, joint, and Revolute Joint. Now, since our joint is connected to a sphere that doesn't have any physics, we can actually hit play and our sphere that does won't drop. So that's kind of cool. But what I'm thinking about is trying to make this orbit the other sphere. So we create a joint that allows it to orbit. So let's switch our axis to Z and take our joint and move it over to the center of our original joint or original sphere. And with that, we're not going to see anything happen if we hit play because there's nothing there. We might if we change the axis. And if you change the axis here, just so you know, we can change the axis to Y, but you won't see it when the simulation is running. You have to stop it and then hit play again. And now you can see the joint works, but with gravity. But what I'm wanting to do is create that orbit, like I said. So in this case, we need to add the drive. So let's go add physics, angular drive, and we'll create that dampening again. Just let's go about 10,000 or so. And we'll hit play. Nothing's going to happen just yet until we slowly increase the velocity. And now we can see we are starting to create an orbit style scenario where you could almost simulate a solar system. Ooh, could you imagine that with the lighting and everything? Have the sun. Oh man, this has just got lots of potential. So, and this isn't even robotics. This is more like science physics now. So that's kind of cool. Could you imagine? You can just imagine where to go with this. So that's what I love about reverse engineering things, is just kind of fiddling around with the settings. You're like, wait a minute, this wasn't in the examples. This gives you some ideas. So all right, let's move on. Now that we have this open, we can click the prismatic joint and see sort of how it's constructed. And you can see that there is an upper limit. Let's go to the parameters here. The prismatic joint has the axis just like it had before, where you can change the axis and see the different directions that you can run this thing. But in this case, let's leave it at Y. You've got a lower limit set at -50-ish, and then an upper limit set, which is off to the right just a smidge. We can reduce that. And then we have a drive on this, so you can see that this particular one is using a target position as opposed to velocity like we did before. So if we hit play, we're going to hit that max position. We've lowered our upper limit to 43, so let's go ahead and bring this down to like 20 something. So now you can see that the target position is somewhere around 20. Now we can add velocity to this, but I think that's where you really need to have that dampening. And you can see now it's got more force behind it. So let's stop the simulation and hit play. Boom, that is much more dramatic effect as opposed to bounce. It goes and it sticks. If we remove that dampening, it just slides, kind of bounces back and forth. So, and the stiffness, you know, what happens if we remove the stiffness? Boy, it just goes all the way. Now we're hitting that. See, as we play with these settings, you can tell the difference. Well, I guess because it wasn't. Let's add that dampening back. There we go. Now, if we take that away, it's going to just fly back, I'm guessing. No? Maybe not? No? Sometimes things don't work the way you think. Hit play. All right. Well, that's kind of what reverse engineering does. You get to poke around. You can see that some things work, some things don't. You can see that you can set your upper limit and lower limit with these arrows so that you can actually see where they fit in the scene with these little ghosty beams. That's an official term, ghosty beams. And if we were to switch the axis here, let's change this to Z and let's hit play. Now it just drops. And that's because we don't have any dampening or anything. If we were to put the dampening on like we had, make sure that number is extensive, then it slowly drops. If we were to put the velocity to a negative amount, like -20, hit play, maybe that's not enough velocity, and maybe I'm not heading in the right direction. Maybe I need to make it 50. There we go. 50 actually brings it up, so a positive number brings it up. So we'll let it fall, and then we can slowly, this is where once you get into like control scenarios where you're dynamically changing the velocity, you can do different things with this. So in this process, like I said, we can change the axis. Let's try X now, but you can't see it until you stop the simulation and start it over. Beam doesn't go anywhere. We'll go ahead and remove the dampening, remove the velocity. It doesn't really know where to go. So let's add that velocity back up and add the dampening. I don't know, I just hit a 1 and a bunch of zeros. It's somewhere like 10 billion is what I've seen. You can alter this. The higher it is, the better. Sometimes you just need a little bit depending on the joint. And let's make this go to a negative. There we go. So now you can see as we control this, we almost have sort of like a mechanical 3D printer sort of scenario. So you can see how this beam could be, or prismatic joint could be used for that. So to really put this to the test, stop the simulation, delete this prismatic joint that came in the simulation, select box 0, control click box 1, go to create, physics, joint, prismatic joint, and there again, same thing as before. The joint is in the center of this beam. You hit play, nothing happens, and that's where we need to move the joint where we want it. And you can see it makes it a lot easier when you're actually, let's do that. Let's delete this joint again because I was getting distracted by the fact that what if I wanted box 1 closer? If I knew that I wanted it closer, we would just basically start off with it that way, so that when we create our new joint by control clicking box 1, hit create, physics, joint, prismatic joint. Now when we move this here, we can come down and set, I want to have collision enabled, and I'd like the yeah, let's keep the x-axis and set the lower limit to 50, since that's what it was, or -50. -50. And the upper limit to 50. There we go. Whoops, I'm using the wrong axis. I think I want Y. There we go. Now what happens if we hit play? Probably nothing. Why is that? Because we don't have a drive. So let's right click, add, and linear drive. And now that's where I can say, do we want a target position of 20? 30. And it's not doing anything. Interesting. Do we need to bump up the stiffness? That did something. So there's something between the stiffness and the dampening that I really need to wrap my head around, because between these two, if would we have gained anything by just adding dampening? Let's try this again. Run the simulation, no stiffness. Double click the dampening and add 100. Nothing happens. So that is the thing that's a little confusing, is when do you use stiffness and when do you use dampening? That's a little bit of homework for myself and for you if you want to learn more about that. But what we did find, this particular joint does need stiffness as opposed to dampening where the Revolute needed it. I don't know. Got to understand motors at their foundation, I guess, is really what the goal is here. So I think at this point, that's enough about the prismatic joint. You can still see the errors if you were to just take box 1 and stop the simulation here and move it into a weird position. You can hit play. It'll jump, and you'll start to see warnings come up about the prismatic joint jumping. But I was hoping to show, there we go, the red arrow here that actually calls out that you've made a mistake. You don't want to do that. If you were going to keep the beam here, you must come into the joint parameters and adjust this so that you can bring those joints together. Let's do that really quick. I don't have a lot of screen to scroll up. Let's just set it to 50, 100. But you get the drift. And we can bring this one down a little bit until those come together. And once that red arrow goes away, then you know you're good. And then you can hit play. And it will function up there if that's how you need your joint to be simulated. I think a lot of these simulations that you're going to find as we get more into the advanced stuff is that it's about replicating something that's happening in a real world environment while balancing the amount of CPU, GPU, all your power that you're going to need to run the simulation. We'll talk about that later. For now, let's go ahead into the next joint, which is spherical. Okay, so the spherical joint was one that I got a little confused by. I get that a spherical joint is basically something that you can adjust the, cone, we'll say, so that you can have the range of the movement that needs to happen. And what I found is if I hit play, the beam falls, but it's really hard to figure out how to add any kind of drive to it, because if I go and add physics, and there you can see an X, Y, and Z rotation property, if you apply these, there's a alert saying that it needs to be an articulation, and I'm not digging into articulation in this video. So what I thought I'd do is show you what I figured out, which is take another beam, which I have here, just a cylinder, which currently doesn't have any physics applied to it whatsoever. If I right click that and say add physics with collision, now that beam drops to the ground, and I can use it to knock, well, smack this thing around a little bit. There we go. Now we can use it to knock this beam around and start to see some of this rotation. So you can, that's how I found to best play with it, was just sort of get a feel for what the limits were. I don't know. Like I said, I'm going to have to start learning articulations and understanding how that works with this joint so that you can actually drive it like you would a shoulder. And even if you grab this one and move it, it's not... Oh, there it goes. Now we got it. We can swing this thing around all day long until it goes crazy and then our simulation breaks. But overall, I have not figured out how to drive this particular one yet because I haven't dug into articulations. That could be another video that we explore. But I felt like that was at least a good overview. It's really pretty straightforward. Just delete, if we want to recreate this, delete it, click on box, control click on box 1, right click and create the joint. Spherical, and then again, just like always, it ends up in the center of the original, or like the beam here, so we can just pick that up and move it back to where we want and come down here and alter the axis if we want, or we can bump up the angle a little bit, like let's go to Y. There we go. If we want to go Z, let's go back to this, sorry. You have to really zoom in and see. Hey, where did it go? There it is. My mouse is acting a little funky. So you can zoom in and see where that's at. If we hit play, what happens here? It just kind of stops, and then we should be able to move this whole thing around again and just see the range. But again, it's just changing the axis. Alright, so we have lots we can learn about the spherical joint and understanding how all of that works, but this seems like a good segue to take us to the D6 joint, which is essentially a mechanism that allows you to custom make joints. You can control the parameters here. For example, they show you that this is the basic D6 joint usage. You can set it so, like right now, rotation Y is unlocked. Any of these others are locked. If I hit play, not much happens. And if I lift this beam, nothing seems to happen. So it's a little confusing what's going on. If I change all these so that they're not locked and load that scene, because that's actually how you do it. These are the parameters for your next scene. Then you can hit play and it'll drop, and it looks a lot like that ball spherical joint. Very similar. You click on that, you can come here and you can limit the different parameters on the, like how much it bounces, whether or not there's stiffness or dampening. This is, again, just something that's going to be outside of the scope of this video because there's a lot to it, but if you've got some custom movement that you want to make, this is the joint to make that. In fact, we're going to use this as an example to go to the rigid body ropes, because if you look at that example and you click on the rope itself, joint, it's a D6 joint. That's what it uses. So you can set up this scene with multiple ropes. You can set the parameters, how long they are, how many you have, and then when you hit play, they just fall to the ground. But that is literally the D6 joint in action. So let's move on, because honestly, this is a whole nother category that is outside the range of what I'd planned for this video. So let's hop over to the distance joint, which is one of the easier ones to understand. If you play the simulation, it lets the beam hang, and you can move this beam around wherever you want. And really, that's all it's for, is just sort of like a connection between these two to ensure that you don't get too close or don't get too far, and you get to control all the parameters of this joint. Clicking down here, I can come over, let's see, we can actually make collisions happen. And let's see, minimum distance, let's do maximum distance, let's tighten it up so you can bring the beam closer to you. Maybe this is like a wrecking ball kind of scenario, or I don't know, you're trying to lift something with a crane and whatever's underneath you is going wild. You might want to be careful. You can exchange the minimum distance out here so that it stays out. And then again, it's really nothing more than just kind of towing it along. Pretty simple, Not a lot to it. Let's just go through the process of stopping this and deleting. You can see that I moved the red beam and now they're showing you the warning that you get. If I delete this, let's leave them in this weird position just to validate that. Control click on box 1, right click, validate that the position works once you've started the joint or created the joint with them in place. I can't seem to control my mouse today. My mouse is doing funky things. I think I need a new one. Let's see, where are we at? Distance joint. Ends up in the middle of that. If you move this anywhere, nothing happens. Kind of interesting. But what's interesting here is there's a joint frame. That was something I don't recall noticing, so let's go back to the old view just so that we load this thing up again. There was no joint frame. It's actually attached to box 1 and box 2. Oh, okay. Sorry, 0 and 1. I'm so used to arrays, I guess. That's interesting. So there's a joint frame. Well, these specialty joints are definitely something that I hadn't dug too far into, and you can see there's plenty to learn here. So if I were to recreate that, I think I need to create the joint frame to be able to do that. So let's try, if I just delete this joint. Let's see, these are connected here. It's outside. Let's see what happens. Do this live. Delete. Does it work when I click and create physics? Whoops. Man, the mouse today. Physics. We don't think we need that. We're not adding physics. We're creating the joint. Distance joint. Now it ended up underneath this, so that's an interesting little detail that I didn't prepare for this video. So what happens if we click this and then go create physics, scene, joint, distance joint? Okay. Yeah, so there's something about this that I don't understand. Let's delete this here. What happens if we just create a physics joint? You can't. Interesting. How about box 1? Create physics joint. Can't do it. You gotta have distance joint. Same thing. Huh. Very interesting. Well, let's see if... Huh. Well, I know we can add the target of box 0. I don't want to scroll through all that. I think we need to add it. Ooh, actually, let's do this. Double click. And let's look at the parameters that were already on this. We have the box 0 joint frame and the box 1 joint frame. So if we delete it, I just want it to act the same as before. So if we click, because we cannot create one without the joint, without something being selected, and you can do this and then create the joint, distance joint. We show box 0 and box 1, which we don't want. We actually want this outside of here. And let's just manually set it, I guess. I don't know. Kind of interesting. Gotta go down to the bottom. Box 0 joint frame, select. And box 1 joint frame, select. And now we're at least set up with what we had before on the same connection to the joint frames. And then I think what we can do is just move this back. Get this out of the way. Get out of the way. This thing can get in the way sometimes. Joint. Move it here. What happens if we hit play? We have that little glitchy thing that I have going on because of my graphics card. I think we got it. Yeah, okay. There it is. So that was an interesting thing to learn live, was that you kind of need to know exactly how each joint works, and then you can mess with it, I guess. Hit the collision, because I get tired of that swinging through the beam. I like a little more reality than that. All right, so we learned some things. The distance joint is an interesting little thing. I don't really know when exactly I'd use it, but now we understand how that works. Let's move on. Okay, let's look at the gear joint. The gear joint's one of those that when I talked about efficiency versus functional, this is kind of where I think we're heading into that space, where if we look at how this is constructed, we see that there's two Revolute joints, one on each gear, and then there's a gear joint that connects the two. And you can see world gear 0, let's see, yeah, gear 0 and gear 1, and then it actually hinges on the Revolute joint. So gear joint has Revolute Joint 0 and Revolute Joint 1 with a gear ratio, so that when you hit play, they are connected. Now, I guess one of the things about this is the fact that the simulation aspect of this, to have the teeth do the driving, for example, if you look at the, let's see which one of these has a driver on it. This one does. We can slow this down by using the target velocity and have that gear move pretty slow. But what we can also find is that we can tweak this ratio, this gear ratio here, and change it. And now you see the physics, or the actual rotation is not tied to the gears themselves, I guess the physical gears, the teeth connecting. It's based on this ratio, and I guess the calculations that it would take to get that just right so that you could truly use the teeth is intense, and so this is a balancing for performance issue. Even this gear ratio is not going to work here. So that is an interesting thing. If I double click this here, so we reload this up and hit play again. I just found that to be very interesting, that I would have assumed that the mechanical aspects of digital twins is that you need to use the teeth to do the movement, but that causes its own side effects. And that is a good segue into the rack and pinion version, where it's very similar. You have, let's see, we have the Revolute joint for the gear itself on the bottom, and then there's a Prismatic joint for the bar on the top. And then there's the rack joint, which ties them together in a similar way. So if you hit play here, you can see the rack and pinion rotating, or the gear rotates and pushes the rack. So we can come down here and change the ratio again, and the teeth will get messed up. But it's probably better to keep the ratio where you need it, and then come down to the drive and then just alter that. So we can say, let's go target position is what they're using. So what if we turn this off and we set target velocity to 50? What happens then? Let's go ahead and hit play. Nothing is happening, and we've got stiffness up to 100. What happens if we hit the dampening? There we go. Now we're moving. And if we change this to negative 50, you can see clearly it's not reality. These things are not actually connected whatsoever, but it does work for simulation purpose. And that's why this is one of those more advanced, customized type things to mimic something within a simulation without grinding your machine to a halt. Okay, the only other example we haven't gone through was the joint break, which is like I'd shown earlier, where you can see the stress on a joint. You can actually watch this break. So let's say we've got a fixed joint here. I'm not going to go into too many details, but if we play the simulation, you can see that it causes the joint to break. And that is exactly what you can do with all your fine tuning of the settings and things. They've got a break force set, and then when this hits, there's a code that changes the color. You can actually open up all the code when you hit this open source button, and you can check all that out. And you can even dig into these examples. If you create something, save it as a USDA, then you can look under the hood how the USD is created, because USD is amazing. I just absolutely love it. So I think that's all we're going to cover today, because you can play with the different parameters to get your joints to break according to reality, and that's kind of where you're going to get some math, and I'm going to stay away from that today. So if you're interested in looking at the tables that I've created and shown here, showing the standard joint types, the fixed, the Revolute, the Prismatic, and the Spherical, or the specialty joints that do all kinds of interesting things, I've got this written up as an article, just a short article on my blog where you can actually see those tables if you're interested in checking those out. Link will be in the description. Other than that, I hope you found this useful as a decent overview for the examples of the joints in Isaac Sim, and I hope that you found this valuable. Thanks for watching.